Most of our decisions involve comparing a limited number of outcomes and finite expected utilities. But do our rules for making rational decisions under risk hold up when infinite quantities are part of the decision problems? If you're already familiar with Pascal's wager, you should expect to see that they won't. In this lesson, we're going to explain the St. Petersburg paradox and show how the principle of maximizing expected utility can yield questionable guidance when infinity is involved. We'll then look at several responses to the paradox. And finally, we'll consider the implications of the St. Peter's paradox and Pascal's wager for the principle of maximizing expected utility and decision theory a little more generally. So let's lay out the paradox. The core of the paradox is driven by our rule for determining the fair price of a gamble. Remember from lesson 11 that the fair price of a gamble is when the price makes it so that the expected value of playing the gamble and paying the fair price equals 0. So whatever you should expect to get from the gamble, you should subtract your fair price from that and get an expected value of nothing. We'll calculate the fair price in a minute. But first, let's lay out what the gamble is. We're going to flip a fair coin until it lands heads. Let's say, here are how the possibilities could be. One way it could go is I flip the coin, it lands heads on the first flip. If that's the case, you get $2. If I flip the coin and it lands tails the first time and then heads on the second flip, you get $4. If I were to flip the coin and it was tails and then heads on the third flip, you would get $8. And so on. The amount of money you can win increases the longer you have a streak of tails before the coin lands heads. So, if you look at these potential payoffs, what do you think you would pay to play this game? As before, I would suggest pausing the video for a minute and considering your answer. How much would you expect to win if you were playing this game? And what's your reasoning? Now let's do the math. We'll use our expected value formula to show the actual fair price of this game. So, since, as we said before, the difference between the fair price and the expected value should be 0, the expected value will just give you the fair price of the gamble. The expected value of this gamble is gotten by multiplying the amount you win if the coin lands heads for the first time on that flip times the probability that that flip lands heads and all the ones before it landed tails. If we look at it, the chance that the first flip lands heads is 1/2, and then you would win $2. The chance that the second flip lands heads after the first one lands tails is 1/4, and you would win $4. It's not written here, but the chance that the third flip is heads and the two before were tails is 1/8, and in that case you would win $8, and so on and so on. When we add up the weighted value of each outcome according to our expected value formula, we learn that this gamble has an infinite expected value because each outcome has a positive expected value of 1, and there are infinitely many possible outcomes. Since its expected value is infinite, you should be willing to pay all the money that you have to play this game. But now think back to your answer. Does it really seem likely that you get much in return from playing this game? As with the Allais paradox, there's a gap with the St. Petersburg paradox between what people think this gamble is worth and what our normative decision theory says the gamble is worth. So if we characterize this problem descriptively, we see that most people aren't willing to pay that much to play this game. Normally, they say they're willing to pay around $4. And that's because you basically have a 3/4 chance of winning less than $4. Normatively, though, our guidelines for decisions under risk tell you to maximize expected value. And the expected value of this game is infinite. So you should be willing to pay all the money you have to play it. But again, it doesn't really seem like you should be, especially since the game could have only a 1% chance of yielding you more than even $100. When we looked at the Allais paradox, it was a bit easier to reframe that problem to show that people were reasoning about it poorly. And then we could show that the guidance of our principle of maximizing expected utility did in fact make sense as a way to respond to that apparent paradox. The same can't really be said for the St. Petersburg paradox. And you'll see that once we consider the various replies. The first attempt at responding to the paradox is just to dismiss the possibility of the game. The game is impossible. There isn't an infinite amount of money and time to play it. But even if there were not a limit on the amount of money available for you to win, you would still be very unlikely to win much of anything. And that really seems to be the driving force of this problem. The second response to the St. Petersburg paradox involves limiting the numbers of outcomes a decision maker should consider. So people who respond this way say we should ignore any outcomes, like the outcomes where we win a really large amount of money, that are highly improbable. The problem here is that any lower limit we assign to the probability of an outcome worth considering seems like it would be ad hoc or arbitrary. We don't want our decision theory in general to ignore highly improbable outcomes, because in lots of other cases it's super important for decision making to consider highly improbable outcomes with significant consequences, which is exactly what this game has. So this seems like a bad way to respond because it doesn't generalize well to the kinds of decisions we normally make. Our third response, I think, is a bit more compelling. It relies on a reasonable understanding of how people actually value money. So this response tells us we were wrong to approach the St. Petersburg paradox by calculating its expected value. Instead, we should calculate its expected utility. And that's because there's going to be a limit to the amount of expected utility an individual can have for this gamble, because money has a diminishing marginal utility for people. So if people's value for each dollar drops off enough, which is really quite plausible, they will value the higher and higher bets less and less, and that will put a finite limit on the expected value of an outcome. And in fact, if we assign the utilities in the right way, we can get it so that the expected utility of this outcome is about equivalent to the expected utility of $4, which is about what people say they're willing to pay. So in this calculation of the expected utility of the gamble, we're using not $2, $4, $8, etc., but the utility of $2, the utility of $4, the utility of $8, and so on. The utilities for more money increase each time, but they increase by smaller and smaller increments, more and more slowly. This actually gives us a small finite expected utility for the gamble. And in fact, in this case, we've set up the scale so that the expected utility of the gamble is about equal to the expected utility of $4. So is the paradox solved? We just have to focus on expected utility instead of expected value? Well, no. So even if money does have a diminishing margin of utility, we can just modify the game. We can turn it into one that actually has the same implications as the original game. We just have to imagine a new version where the payoffs increase more rapidly in a way that overcomes the decreasing margin of utility of money. So the utilities of each outcome just have to be high enough to overcome how unlikely they are. And we can get that if we have higher and higher payoffs so that they increase commensurate with the unlikeliness of the outcomes. And if we set it up right, the expected utility of the gamble will add up to an infinite value again. So focusing on utility can get us away from the original version of the paradox, but there's a nearby version that replicates the original problem. The fact that we can come up with a modified version of the paradox that helps revive it draws attention actually to the real issue involved with it. In both formulations, the key is that the expected utility of the gamble seems unreasonably high given what we feel the gamble is worth. And here's the real kicker. While the expected utility of the gamble is infinite, every outcome can only ever grant the player a finite amount of money, even the really unlikely ones. So if you should be willing to pay the expected value of the gamble, or the expected utility of the gamble, why should you be willing to pay more for the game than it's possible for you to win? If the responses to the St. Petersburg paradox aren't really satisfying, and similar problems around infinity can be raised with Pascal's wager, what should we take away from these puzzles? They both show that there are unresolved issues around whether we should be guided by the principle of maximizing expected utility when infinity is involved. Does this mean we need to question whether it's rational to maximize expected utility in general? Probably not. In most of the decisions we make, we're not involving infinite quantities. So maximizing expected utility makes sense. And does it even make sense to consider infinite utilities or infinite expected utilities? Or is there a limit to how much utility a person can get from an outcome? With money, it seems quite reasonable to think there's a limit to our utility for money. We can only spend so much of it. But that might seem less plausible for other things that we value. Our relationships with others, the experiences we have, the enjoyment we find in things we do. It seems easier to argue for those that they could have even an infinite amount of utility for us. But on the other hand, we are finite beings with finite minds. So maybe there's only so much utility that we can have. If there is such a limit, though, how would we determine it? It's not clear what would indicate what the limit to a person's utility is. And that wraps up our study of decision theory. So you should now be able to distinguish decisions under risk from decisions under ignorance, and know how to use several rules for making decisions under ignorance, including dominance, maxi-max, maxi-min, and the principle of insufficient reason. You should be able to distinguish normative and descriptive decision theory. You should be able to characterize what the Allais paradox shows about how people do make decisions. And also, you should be able to understand how to characterize the rational decision in the Allais gambles. And finally, you should have an understanding of how the St. Petersburg paradox and Pascal's wagers show the complications that come from trying to calculate expected utility when infinity is involved.